Hello and welcome to Chapter 4, Section 5, Part 2. Today we are still dealing with U sub, so we're doing integration with that whole substitution thing. But now it's like slightly more complicated, so we're also adding in this thing called a change of variables. So here we go. Alright, so this whole change of variables things needs to occur whenever we use that like u part, whatever we set as u, when we take the derivative of it, if it doesn't really end up somewhere else in the problem, because that's how we were doing u sub to begin with. We would be able to recognize it because whatever u was, when we took the derivative, it would be elsewhere in the problem. So this is an issue. So like for this problem here, I have the integral of x times square root of 2x minus 1 dx. So for this problem, u would probably be the most complicated part, the stuff that's usually in parentheses, and here for us the parentheses is kind of like the square root, because I could really rewrite this as the integral of x times 2x minus 1 raised to the 1/2 power, because you know how radicals are just exponents. So the stuff inside my parentheses would be my u, which is the 2x minus 1. But when I find du here, the derivative of 2x minus 1 is just 2 dx. But if you look back at the original problem, I still have this x out here that like I wouldn't be able to rewrite in terms of u. Because remember, the whole point of u sub is to be able to write that whole entire original problem with just u's instead of x's. So when this occurs where my du isn't somewhere else in the problem, then we're going to use this thing called change of variables. And to use change of variables, all we're doing is rewriting the u equation. So I originally said u equals 2x minus 1. I'm actually going to use that to put this in terms of x. So I'm going to add 1 to both sides to get u plus 1 equals 2x, and then divide both sides by 2. So that x equals u plus 1 divided by 2. So now, looking back at the original equation, I'm going to use the x times 2x minus 1 to the 1/2 power dx. Then, I also need to solve for dx. So let me do that. Dx equals du over 2. Okay, so now I can rewrite my original as, instead of writing x, I'm going to write u plus 1 over 2, because that's how I had solved for x there. And then the 2x minus 1 raised to the 1/2 power, well, I said 2x minus 1 was just u, so this is really just u to the 1/2 power. And then we said dx was really du over 2. So now I have my original equation all written out in terms of u. So I can integrate this now by kind of simplifying it down, multiplying stuff out, all that good stuff. So I'm going to simplify this into 1/4 because of the something over 2 times the du over 2. Really, it's just a constant of 1/4 times the u plus 1 times the u to the 1/2 times the du. The 1/4 is a constant, so I can actually take that out of the integral and just leave that in front. And then I'm going to rewrite this so it looks a little nicer. U to the 1/2 times u plus 1 du. Okay? And then to make this easier for us to integrate using the power rule, I'm going to distribute my u to the 1/2. That way I have everything in terms of like exponents. So u to the 1/2 times u is really u to the first power. So the exponents would add to give me u to the 3 over 2 power plus, and then u to the 1/2 distributed to the 1 is u to the 1/2. And so now I have two terms that can just use the power rule to integrate. So here we go. We have the 1/4 in front, integrating u to the 3 over 2 power using the power rule. I'm going to add 1 to the exponent and then divide by the new exponent. Same thing with the u to the 1/2. And then plus c at the end. I'm just going to simplify this out a little bit because I'm dividing by a fraction here, so it looks ugly. So instead of dividing by 5 over 2, this is really multiplying by 2/5 and multiplying by 2/3 for my other term. Okay, and then now I can just distribute that 1/4 that was in front. So I end up with 1/10 u to the 5/2 power plus 1/6 u to the 3/2 power. And then we just have to rewrite this in terms of x's now because we're done integrating, so we don't need the u's anymore. So earlier we said u was equal to 2x minus 1. So raise that to the 5/2 power plus 1/6 times 2x minus 1 raised to the 3/2 power plus c. And then I am done. That is my final answer. All right, so I know it took a little bit, but again, the recap of it is once you see what to use for u, if the derivative du is not like back in the original problem, that's when you're going to have to do this change of variables thing. So that you just rewrite u in terms of x's and then plug everything back in. So let's do another similar example. So this time we're doing the integral of x times 3 minus 2x raised to the 4th power dx. So here I already have parentheses, so I already know what I'm going to use for u, this 3 minus 2x. But if I were to take the derivative of 3 minus 2x, I already see the derivative is going to be negative 2. I have this x out here in the other part of this problem, so nowhere in the derivative is x, so that's going to be awkward, which means I'm going to need this change of variables thing. So I'm still going to start out by writing down what I'm using for u, finding du, and then setting it equal to dx so that I can still plug the dx back in. But then because my du doesn't have the x in it, now I'm going to use the u equals 3 minus 2x to rewrite this in terms of x. So I can subtract 3 on both sides and then divide by negative 2 to get x by itself. So now x just equals u minus 3 over negative 2. So I can rewrite my original problem now, all in terms of u. So instead of x, I'm writing u minus 3 over negative 2. The parentheses 3 minus 2x is really just u to the 4th power. Dx is du over negative 2. So same thing again, let me simplify this out a little bit so that I can integrate this easier. So multiplying this out, I have, I just like to separate the fractions. So the negative 2 times the negative 2 is positive 4, so it'll be 1/4 times, then I have that u minus 3 left over on top, and the u to the 4th, and then the du left on top. So moving my 1/4 out, and then the u to the 4th, I can just distribute in here, so it'll be u to the 5th minus 3u to the 4th du. And then I can just integrate that now using the power rule. So it'll be u to the 6th over 6 minus 3 times u to the 5th over 5 plus c. And then multiply everything out with the 1/4. And I'm just going to, save myself some time here and replace the u with my 3 minus 2x. So this will end up being 1/24 times u, which is 3 minus 2x raised to the 6th power, minus 3/20 times 3 minus 2x raised to the 5th power plus c. And there we go. Not too bad. Alright, so now I want to move on to the next thing, which is solving our integrals where they actually have endpoints, or definite integrals. Remember, definite just means there's like an ending to it, so you don't do that plus c at the end. So if we have endpoints to it, this is where we would have to like plug stuff in and then subtract at the very end. So we're just going to integrate like we normally would. This does require u sub though, because if you look at our problem, we have slightly more complicated. We've got a square root here with stuff inside. So if we use u sub here, then u for us would be the x squared plus 3, because that's like the stuff inside the radical. If you think about it, it's like, the parentheses x squared plus 3 raised to the 1/2 power, so that would be our stuff in parentheses. The derivative of this, of the x squared plus 3, would be the 2x, which does also exist in this problem, so we don't have to do that whole change of variables thing. So this is kind of nice because we now have a good contrast between like our change of variables stuff with using u sub like normal. So I'm just going to start off this problem by rewriting that square root into an exponent of 1/2. And then I'm going to use u equals x squared plus 3 because that's the stuff inside the parentheses. So I'm going to go through my regular process of finding du, which is 2x dx, and then getting dx by itself, which is du over 2x. So now I can rewrite my original problem in terms of u. So I'm going to keep the 0 and 3 endpoints for now, but keep in mind these endpoints were when this problem was in terms of x. Okay, so keep that in mind because when we're writing the rest of my problem in terms of u, I'll have that 2x there, but then it'll cancel out when I multiply it by the dx, which is du over 2x. And then this leaves my problem in terms of u, so that it's just 0 to 3 of u to the 1/2 du. So this I can easily integrate using the power rule. So u to the 1/2 would become u to the 3 over 2 over 3 over 2 power plus c, except we have endpoints, so we're not doing this plus c thing. Really, we are now plugging in our endpoints of 0 and 3. But again, keep in mind these were x values. So I just like to write that little x there to remind myself these are x values. I can't plug them into u. That's the problem. So because my problem is still in terms of u, I can't plug this in or plug in my endpoints of 0 and 3 until I've replaced the u with the x squared plus 3 that we started out with. And instead of dividing by 3 over 2, I'm going to multiply by 2/3. So now I can plug in my endpoints of 0 and 3 and then subtract. Or this is my preferred method, but you don't have to. Right here where we integrated u and then we still have our endpoints in terms of x, I can actually turn my endpoints so that they're in terms of u. Earlier we said that u equals x squared plus 3, so really I can plug in x into my u equation to figure out what these endpoints would be in terms of u. So if I plug in 0 into u equals x squared plus 3, that means u is going to equal 3 because 0 squared plus 3 is just 3. And then if I do the same thing for the 3, I get u equals 3 squared plus 3 is 12. So if I change my endpoints so that they are in terms of u, I don't even have to plug the x's back in. I can just plug in 12 and 3 into my u integration and then subtract from there. So I'm going to do that first. This will end up being 12 to the 3 over 2 power times the 2/3 minus, and then I'm going to plug in the 3 to the 3 over 2 power over 3, and then I can solve from there. If you don't like it solving for u as endpoints, you can always just plug it back in so that the u becomes the x squared plus 3, and then plug in the 3 and the 0 in for the x here. So 2 ways to do it. They both come out to the same answer at the end. It's really up to you. So this would be 3 squared plus 3 raised to the 3 over 2 power minus 2 times 0 squared plus 3 to the 3 over 2 power. And for this problem, actually, it comes out to exactly the same thing. So we still have to solve out the 2 times the 12 to the 3 over 2 power minus the 2 times 0 plus 3 to the 3 over 2 power, which is exactly the same both ways. Sometimes it's easier by solving for u first as endpoints. Sometimes it's easier plugging in the x's. Again, it's whatever you're more comfortable with. You get to choose which way you want to do. All right, so simplifying this down a little bit, I plugged in, I rewrote the 3 over 2 power as the square root of that number raised to the 3rd power, because that's really what an exponent, that's a fraction, is going to do. Then I simplified my root 12 into 2 radical 3. And then when I cube the square root of 3, I end up with 3 radical 3. So that's easy to multiply out into 6 radical 3 over 3. On the other term, I have the 2 radical 3 raised to the third power. I'd raise the 2 to the third power to get 8, and then the radical 3 to the third power would be 3 radical 3. And then multiplying that out, I end up with 48 radical 3 over 3 minus 6 radical 3 over 3 gives me 42 radical 3 over 3, which reduces to 14 radical 3. And that would be my final answer. Quick throwback to our square roots and being able to simplify those. All right, let's do one last example. So for this problem, we have the integral from 1 to 9. So this is a definite integral since there's endpoints of x over 7x plus 1 raised to the 2/3 power. So real quickly, I've got exponents, I've got parentheses here. The parentheses is what I'm going to use for u, but when I take du, the derivative of the parentheses, I end up with 7. So this x kind of is out there by itself now, which means I'm going to need that change of variables thing. So let's start. U equals 7x plus 1. Du will be 7 dx, so dx equals du over 7. Okay, but I know I'm going to need that change of variables thing, so I'm going to go ahead and solve for x here. So u equals 7x minus 1, I can subtract 1 on both sides and then divide by 7 to get x by itself. All right, and from there, I'm going to, since I have endpoints, I'm actually also going to solve for u for my endpoints. That way I have everything in terms of u. Because remember, our endpoints start out in terms of x, so to plug them into the u equals 7x plus 1 equation, that'll give me endpoints in terms of u. So plugging in the 1 into 7x plus 1, I end up with 8. And plugging in the 9 into the 7x plus 1, I end up with 64. So now rewriting the rest of my problem, the x on top, I'm going to rewrite as u minus 1 over 7. And then actually, instead of dividing by this stuff, I'm just going to write it as a negative exponent. So I have u minus 1 over 7 times the 7x plus 1 will be u raised to the negative 2/3 power instead of the 2/3 power here. I'm just making it negative so that it ends up at the bottom of the fraction. And then dx will get replaced with du over 7. Okay, so just like before, I'm going to multiply things out, simplify it, distribute, so that I can make this look nicer. So my endpoints are now 8 to 64 of 1 over 49 times u to the negative 2/3 power times u minus 1 du. Let's distribute this. Actually, let's first write the 1 over 49 on the outside of the integral. And then let's distribute my u to the negative 2/3 times u minus 1. So adding my exponents for u to the negative 2/3 and u to the first power, when I add my exponents to multiply, I end up with u to the 1/3 power minus u to the negative 2/3 power when I multiply that by 1. Okay, now we can use the power rule to get u to the 1/3, add the 1 to the exponent will give me 4 over 3 over 4 over 3, minus u to the negative 2/3 plus 1 is going to be 1/3 divided by 1/3. Okay, and then here, at this point, I don't need to plug u back in because I already changed my endpoints into terms of u, so I can just plug these in for u here. So this will be 1 over 49 times 64 raised to the 4/3 power times 3/4 minus 3 times 64 to the 1/3 power. And then I'm going to subtract that from me plugging in the 8, the endpoint of 8 in for u. So this will be 3/4 times 8 to the 4/3 power minus 3 times 8 to the 1/3 power. Okay, simplifying this out. 64 to the 4/3 power is me taking the cube root and raising it to the 4th power. So the cube root of 64, I believe, is 4. 4 to the 4th power is 56. So it'll be 3/4 times 256 minus 3 times, and then 64th, cube root of 64 is just 4. Minus, and then we have 3/4 times 8 to the 4/3 power means I'm taking the cube root of 8 and then raising that to the 4th power. So cube root of 8 is 2. 2 to the 4th power is 16. Minus 3 times the cube root of 8 is 2. All right, let's simplify this out even more. 3/4 times 256 is 192. Minus 3 times 4 is 12. Minus 3/4 times 16 is 12. Minus 6. Simplifying all of this out, I end up with 1/49 times 174, which doesn't reduce or anything, so just 174/49 is our final answer. Alrighty, there's a lot of simplifying, but we got it at the end. Alright, that's it for section 5. I'll see you next time for section 6 of chapter 4. Thanks for watching. Don't forget to like and subscribe. Bye!